Okay, so section 1.5, linear dependence and independence. Okay, so when you take a set of vectors, so we could say the set, so set theory has, if you put items in a set, you put a curly bracket, and then you can list them inside the set, and it means the order is not important. So this is a set. Okay, so just another way to write a group of vectors. Okay, we can write them as a linear combination. So what does that mean to do? So linear combination is when we add or subtract a multiple of those vectors. So we might say A times 1, 2 plus B times 3, 4. And we're going to set that linear combination equal to the 0 vector. Okay, so which is just the vector the same size. All right, so when we solve this linear combination, we'll get values for A and B. Okay, so can someone tell me what the easy and obvious solution to this linear combination would be?
0, 0.
0, 0. So A and B are 0. Now, could there possibly be another value of A and B that aren't 0 that makes two vectors add or subtract and turn out to 0? Sure. Maybe for this or maybe not. Right? I can't see one right off, like if you multiply this by 3, this by minus 1, then the top one will disappear, but the second one won't, right? So maybe there's no answer other than 0, 0, okay? So if A equals B equals 0 is the only solution, then we say the set S of vectors is independent. I just wrote it. I'm not getting it. Just if we have a linear combination equal to 0, this is the definition. So yeah, like just 0 always. Yeah. Yeah, so this is just part of the definition is that if you have a linear combination equal to the 0 vector. Okay. Oh, well, what two numbers when you add them together give you 0? 0 plus 0 will give you 0.
Okay, so you're not referring it at all to like the vectors themselves, it's just A plus B? Like 0 plus 0 is... Oh, yeah, okay.
So if you put 0 in here, then you would multiply, and that would be 0, 0.
Mm-hmm.
And then if you put 0 here, you'd multiply and get 0, 0, right? Do you see it? Yeah. Yeah, so that's just one possible solution. There might be more solutions that of numbers that we could put for A and B that when we add these together, we'll get 0, but we don't know that. But if the only solution, we're going to figure that out after, if the only solution is 0, 0, then the set of vectors is independent. And if we can find A and B so that they're not equal to 0, then the set is dependent. Okay, so that's the definitions. So basically, if you're asked, is this set of vectors dependent or independent, you set up the linear combination with the zeros on the other side, and then you solve for A and B. And depending on what the solution is, you can answer whether it's dependent or independent. So if the only solution you get are zeros, then that's independent. If you get something other than zero, then it's dependent. And that would answer the question.
What do you mean by dependent and independent?
That's what they mean, is independent means that the only solutions to a linear combination equaling zero is zero. Yeah. And dependent means they can actually depend on each other to get another answer. But these ones have nothing in common that you can. So if you think of parallel vectors, right? If you think of the vector, for example, 1, 1, and 2, 2. So if we took those, whoops, and we did this, 0, 0 still works, but there is another answer. What would be another answer that would work? If we let A be 2 and B be -1, that would work? Yeah, is there another possible answer?
A negative 2.
Okay, so here's one answer, A -2, B is 1, that will work.
And 0, 0.
0, 0 works. There's more. What's another one?
Maybe A is 4.
Sure.
B is -2.
Yep, that will work. And we could go on forever. So when it's independent, the only solution is 0, 0, but when it's dependent, there's infinitely many solutions. You can go on forever. Because something like this is happening. They are related to each other. Okay, and that's what we call dependent, is when one is like a multiple of the other, but in R3, it won't be as obvious, maybe. Okay, that they're... Okay, but that's what dependent and independent mean. Okay, so this would be dependent, because there's more than one solution. Okay, so let's look at the 1, 2, 3, 4 example. So the solution for this, we set up the linear combination. So when we ask, is it dependent or independent, this is all we're asking, is when you solve this linear combination, can you get answers other than 0? So you would write out the equations. So this will be 1A plus 3 times B equals 0. And the second one will be 2A plus 4B equals 0. So what might we do to solve this? Multiply the top one by -2? So if we do that, we will get -2A minus 6B equals 0 times -2 is still 0. And if I write this one, add them together. Minus 2A plus A cancels, which is what we were doing. Minus 6B plus 4B. Solving for B. B equals 0. So what do you think that means? Yeah, so if B equals 0 and we wanted to find A, plug it into either equation, it doesn't matter which one. So A and B are both 0, so it's independent. So that's what will happen if it's independent, is you get the answer 0. And in fact, did we really need to do this? No. Now, if it was in 3, R3, and you get 1 as 0, that doesn't mean all of them are 0. Okay, so, for example, let's make an example that we don't really need to solve, that we're going to look at. Okay, so let's say the same question, but with these 3 vectors. Okay, so I tried to make it very obvious that 2 of them are, these are parallel. Right, you see that? They're parallel. This one is not. Right? So, you don't need to find all the answers or even the general solution for the answers. If we set this up, all zeros work, of course, it will always work. But is there another possibility here? What if C is 0? Okay, so forget about that one. Just like the example we did on the last page, what could we put in for A and for B that's not 0? We could say A is 2 and B is -1. All right, so then we'll get 2 minus 2, which is 0. Do you see that? All right, here we get 2, 2, 2, minus 2, 2, 2, 0, 0, 0. Okay. So the solution, A equals 2, B equals -1, and C equals 0 works, and so these are dependent. So I did that without solving the system. Yep.
So what we need to know is the solution is dependent or independent.
Yeah, and that's what I mean, that I said earlier, that this section really should be after Chapter 2, because there's, but there is different things. So when we have vectors, we want to be able to find, do these 3 vectors, for example, add together to give another vector of a different type. And if we know that they're dependent, we'll know that there's infinitely many solutions, and then we can use those vectors to form other vectors, right? So this is sort of a check in a list of items that you need to check off for a set of vectors to be a basis. A basis, we talked about earlier, is a set of vectors that span the whole space, which means you can get any answer that you want. Okay? So this is sort of a small piece of a later topic. Okay? So you can do it by setting up the system and solving it, and getting an answer. Or if you notice that there are vectors parallel, you can just comment that it's dependent because of that. And if you had to list one solution, you could pick whichever one works, you know, and there's infinitely many different ones. You could set up the system and solve it, and we will do that in a minute in case you didn't notice that there are vectors that are parallel, and you might try to set it up and solve. Okay. Okay, so example 3. Okay, so here we have three vectors, and I didn't obviously make one a multiple of the others, okay? That doesn't mean that they're not dependent, but we'll set them up and solve it. So you would set up the linear combination. And then write out the equations. So for the first one, we'll have A plus B. There's no C, that's 0, equals 0. No A in the second row, plus B, plus 1C equals 0. And in the third row, no A, 2 B's, 2 C's, equals 0. Now, when you look at these equations, there could also be a hint in here whether they're dependent or independent. Do you notice anything about these three equations?
Yeah, 2 and 3.
Right, 2 and 3 are actually the same, right? When you multiply an equation by a number, it's still the same equation, it's just disguised. So these are actually the same equation, okay? So that's a hint to the answer. But let's look at it. So here we could say A is equal to what? Negative B? And here we can say B is equal to negative C. And if we solve for B here, what would we get? Also negative C. Right? So this is the same thing stated twice. This is actually the answer. And if you remember us doing the span, this is sort of the same thing. If you have A, B, and C as our values, so let's look at it this way. If we had A, B, and C, we're saying that A is minus B, and B is, yeah, we actually wouldn't, if we're going to put B's in here, yeah, so I could put minus C here, but let's say C is what? Minus B? Or, yeah, C is A, you could do that too. So B is B, and C is minus B. If you can get all the same letter in here. All right, so what did I just do? I said, well, A is minus B, so I'm going to replace that. B, I wouldn't replace because I'm going to put B's in it. So B is just B. And then what's C equal to? Well, C, if I rearrange this, C will be minus B. So here's the vector that is the solutions here, right? So it's a bit different than span because we're looking at these. We'll write it in vector form later in another chapter. But basically, we have, if we pick any value of B, so if B is 1, that's a possible solution. So we could get, so one solution would be A is minus 1, B is 1, and C is minus 1. What's another possible solution? If we let B equal 3, what would we get? Minus 3, 3, minus 3. And anything like that, we could put B as 0 in, and that's the trivial solution. But we don't want that. We're looking, is there another solution? And we found one. We didn't get any zeros here when we were looking at it, and we could check our answer by just putting one of these in. So write the linear combination. Sometimes it'll say write an appropriate linear combination. So if it's dependent, you would have answers in for A, B, and C. And if you work this out, you could just check if your answer's right. This gives me minus 1 plus 1 minus 0. The second row gives me 0 plus 1 minus 1. And the third row, 0 plus 2 minus 2. So it's dependent, which means there are infinitely many solutions. You could all write a different number in here for A, B, and C, and it would work. If we put the 3's in or 100 in, it would still work. Okay, so we'll do another example. Were you done with that last one? You got it? Or you needed it still? Okay, so set up the linear combination, that's step 1. Write the equations as step 2. Actually, step 1 could be looking through them and seeing if you notice that they're parallel, because then you just know it's dependent right away. But I didn't make them so that would be obvious or not, so set up the linear combination. So A, 1, 2, 3. Zeros on the other side. And then write the equations for that. So A plus 1B plus C equals 0. 2A minus 2B plus 6C equals 0. And 3A plus B plus 5C equals 0. Now, this is not as obvious. Is one of those equations, is one of the equations the same as another equation in here? No. So still not as obvious. That doesn't mean they're independent, though, just because you don't notice anything. So we have to solve. And this is, in Chapter 2, we're going to find a better way to solve it, but right now it just gets confusing. You plug A into, right, and try to eliminate some of the variables. So to solve this, let's call these A, B, and C with a big letter so that when I rewrite them I can refer to which one I'm using. So there's no right or wrong way to do this. I maybe would solve for A in this first equation because there's no coefficients. It looks nice and easy. So minus B minus C. You agree with that? And then plug that into the other two. Then you end up with two equations with B and C in them and no A, and you can solve that. Okay, so solve for one letter in one of the equations, plug it into the other two. So we're going to take this as equation A, and we're going to put it into B, and then we're going to take equation A and put it into C, and this will give us two equations with just those letters in it. So let's do that. So here's 2 times A minus 2B plus 6C equals 0. This is equation B. All right, so I've got my equation. And do the same thing with C. So 3 times A so I was just writing this, and instead of A, I was putting minus B minus C. And then just work it out. Oh, thank you. So minus 3b and plus b is minus 2b. 2c. There. So now we have two equations. Minus 4b plus 4c equals 0, and minus 2b plus 2c equals 0. What do you notice about those? They're the same. So when we go to solve, what will happen? We don't get 0 as the answer, but we do get zeros. If you multiply this by 2, for example, and then you would have, or say negative 2, so plus 4b minus 4c, add them together, and we get 0 equals 0. So that doesn't mean no solution, it just means that they were the same equation. But what does having two of the equations the same mean? They're dependent. But if we wanted to find the solution, we still haven't found it. We didn't find anything. But all this means is if these were the same equation, we can go back to what we used up here, and that's our actual solution. So let me write it out. If these canceled, they're gone. So what we have is A equals minus B minus C. So if we're putting those in, A, B, and C, remember from back when we did it before, you can have two letters in here, not just one. So if A is minus B minus C, then we have two letters in here, so we can have a B and a C. So it just means where the last one, we just had one letter in our possible solutions, right? B, 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 that means you just pick one, plug it in, whatever B is, plug it in, and that's one possibility. To pick a different B, plug it in, and that's a different possibility. For this one, what do we need to choose? A B and a C, plug it in, and that's a possibility. So if we choose, say, B is, I don't know, 1, and C is negative 2. I'm just picking random things, okay? Because it doesn't matter what you choose. Not 0. Because then you're saying 0, 0, 0. Well, we already know that's a solution. That's always a solution. We're trying to find one that's not 0. So I just choose anything. So if we plug them in, we would get A is minus 1 plus 2 is 1. B is 1, and C is negative 2. And then we try it. So back way up to the top to our linear combination, I'm saying A is 1, B is 1, and C is negative 2 will work. Okay, if this works, that means it's dependent. And there's lots of solutions because we can plug in different values for B and C and get different solutions. And does this one work? Did anyone look through? What's the first line? 1 plus 1 minus 2. That's 0. The second line, 2 minus 2. What? It didn't work. We got something wrong. Did anyone notice a mistake anywhere?
I think we can edit the B is equal to C.
Oh.
B.
Oh, B is equal to C.
Yeah.
Yeah, it is. You're right. We have to back up. Okay, so that's good. So what I tell my kids when they make mistakes is what? Nothing would be invented in the world if people didn't make mistakes. So this is wrong, so we're going to go back. I make tons of mistakes. So let's go back and fix it. So right here, we have A is here. So just cross, this is okay, but just cross it off for a second, okay? So wherever you have that part, just go back to right where I had this, okay? So that's where we'll pick it up. So far so good. Thank you for noticing where I missed. And right here, we still need the equation that canceled out. We need one of them, not two, because they are, they're the same, so we need just one of them. So pick whichever one you like better. Okay, so let's write a little note here. We need one of these only, because they're the same. We only need one. We don't need both. So let's write one of them down. Minus 2b plus 2c equals 0. All right, so if we were to solve these now, these two equations, we've got a is minus b minus c. And what do we get from this one if we solve for either b or c?
Choose the equal to
b equals c. Okay. So if b equals c, we can get rid of one of these in a. Doesn't matter which one. Let's replace the b with a c. So we get minus 2c, and now we do get just one choice. So our a is minus 2c, our b is c, and our c is c. Now let's try it. All right, so now we just need to choose c. C equals 1. So we're going to go with a is minus 2, b is 1, and c is 1. Will that work? Hopefully. We'll rewrite it. So minus 2 times 1, 2, 3, plus 1 times 1 minus 2, 1, plus 1 times 1, 6, 5. All right. If we check, so minus 2 plus 1 plus 1, that's still 0, good. The second equation, minus 4 minus 2 plus 6, oh good, so far. Let's see if the third one's wrong. Minus 6 plus 1 plus 5, woohoo! Dependent. Okay. And do not spend too much time on this section. I picked a few questions out for you to try, because we're going to find a much, much better way to solve these equations that's not confusing like this later, in the 2 classes from now. And then we'll go back to it and be able to get the answers really quick and much easier. Yep?
Where we proved that 2 of those equations were equivalent, at the bottom there, would we only need to prove 1, or do you want us to prove all 3?
Oh, definitely all 3. That's an excellent question. So she's saying in this check, should we check all 3? Definitely, because remember that when I got it wrong, I checked and the first line worked, and then I went and checked and the second line didn't work. Any one line could fail, and that would be an indication that you got it wrong. And later on, that when we do it the other way, if you've taken linear algebra before, when we do the row reduction way, if the mistake is in your third equation, when you go to check, that actually means you only made a mistake in one of the last 3 steps. And if the second equation doesn't work, it means that you made a mistake in the middle steps. So you can go back and start from the middle. So it's actually really good to plug them in order. If you make a mistake later on in the first equation, scratch it all out and start again, don't even try, because it just means you made a mistake early on in the question, and then everything is wrong, right? So it is good to check in all 3, for sure. So that's it for that section, right? It's just solving equations and seeing if, that's it. That's all that's in that section. So that's the end of chapter 1. And on the test, there's like one small question, whether it's independent or dependent, okay? And it's really easy to solve. It won't even be, you won't make a mistake like this, because it won't be solving it that way.